So I will talk about the modeling of the SAPS during the storm occurred on March 17, 2013. And I would like to acknowledge my co-authors who provided the data and also very useful discussion. So as you know, SAPS refer to the fast westward convection appeared in the ionosphere, which is equivalent of the typical auroral convection, predominantly in the dusk to midnight sector, and they are observed to be highly structured with width about 1 to 5 degrees in the latitude. And they are believed to be one of the most important MI coupling processes in the inner hemisphere and the subauroral region. And they can influence the ionosphere composition, and they also found to be associated with the storm-enhanced density and the mid-latitude ionosphere density trough, as well as the plasma sphere probe. So this study is to investigate the evolution of the SAPS in both ionosphere and in the inner hemisphere during a storm using a modeling framework. And also we want to assess the modeling capability of reproducing this phenomenon. So observations from soup down show that there's a large enhancement in the westward convection appeared in the subauroral region, which is shown here by the red bars. Although the coverage is not so good at this time. And also overplotted is the DMSP trajectories. And during this time, around the 10 UT, and you can see a spike in the velocity, which is sunward direction. And the color overplotted along these trajectories are the intensity of the auroral precipitation. So you can see this spike appears just equatoward of this auroral precipitation boundary. So that is the SAPS. So we are going to use this space weather modeling framework to model this event. This framework has the basic modules that are necessary for this near-Earth physics. So we have the MHD model, Bacillus, the atmospheric potential solver, and also inner hemisphere model, RAM-ACV, as Vanya just mentioned. So RAM-ACV has two components. This kinetic RAM model computes the kinetic particle distribution at the equator, and it is coupled with this 3D magnetic field code. So they exchange the pressure and the magnetic field self-consistently. The pressure produced from the Rinker model is passed to the MHD model, which solves the ideal MHD equations, and they could not resolve the kinetic physics in the inner Magnetosphere region. And in this MHD code, the field line currents are calculated and they are passed to this potential solver where the electric potential is calculated. And this electric field is then mapped down to this inner Magnetosphere region to provide the electric field, which is used to convect the plasma from night side towards Earth and develop the ring current. So as you can see, the electric field in this framework is self-consistently calculated with the other fields and also the plasma and other global current systems. So this is a storm event on March 17. So it is triggered by a CME-driven shock, which arrives at a magnetosphere around the 6 UT. You see the solar wind pressure enhances here, and the BZ turns southward. And you see the storm sudden commencement here, and the DST reached down to minus 100 in just 4 hours. So next, I'm going to show you some results from the simulation. And the first one is the evolution in the atmospheric electrodynamics. So first current is from top to the bottom are the field line currents and the Peterson conductance, this electric potential, and this is electric field, and this is the convection in the ionosphere. So first current is during the quiet time before the storm enhancement, and this one is during the storm enhancement, and these two columns in the last two columns are during the storm main phase. So you can see from field line currents before this storm, you have a typical pattern of the field line current, and during the storm time, they are enhanced, and also the field line current expand to lower latitudes. And during the storm main phase, you can see the region 2 field line current at a lower latitude. They try to rotate towards the dusk side, and it was original here, symmetrical around the day-night meridian, but now it is rotates to 22 MLT. And this is Peterson current. You can see from here, in the model, the conductance is specified by two components. One is from the solar irradiance induced background conductance. The other one is from the auroral precipitation. So in this model, we specify the auroral precipitation induced conduction based on the field line current. So in the night side, you may notice that the pattern of this conductance is very close, very similar to the pattern in the field line current. So as you can see, after the storm time, the auroral oval expands to a low latitude. But in the subauroral region, the conductance is really low. And this is electric potential. This is a typical two-cell convection pattern. And in the storm time, you can see in the dusk side here, the negative potential cell trying to separate from the main auroral cell and extend to the post-midnight. And this is electric field. So yellow shows the electric field in the poleward direction. Blue is in the southward direction. So you can see there are two electric field enhancement. One is in the subauroral region. The other one is at a higher latitude, as you can see from here too. And this subauroral electric field is the one that drives the SAPS convection in the subauroral region, as shown in the bottom panel here. So the blue is the westward convection, and the yellow is eastward convection. And you can see that there are two west flow channels here. The one is in the subauroral region, the other one is a little bit higher latitude. And this one is the SAPS convection. And also you see the flow extend to the post-midnight and with a decreasing speed. And this is consistent with observation. So now I take a radial cut from the ionosphere. So I fixed at MLT of 19 and plot this as a function of latitude and time. So you can see at this dashed line marks the shock arrival time. So you can see after the shock arrival, the lower latitude velocity is initiated, and then it is enhanced around 9 UT and lasts for a few hours before 12 UT, and it decreases a little bit, and in the later time of the storm time, it is enhanced again. But now this time, the velocity, the speed is a little bit smaller than the previous. So the pink line here shows you, I was trying to separate these two flow channels. One is above 58 degrees, the other channel is below that. So in the subauroral region, this is SAPS. Above that is auroral convection. And the pink line is also put on the conductance. You can see below this pink line, the conductance is really, really low. That means we need a very high electric field in order to satisfy the current continuity. So here is the field line current. So the blue shows the downward, the region 2 field line current. You can see the evolution of this field line current is very correlated with evolution in the convection, because when you see the enhancement in the region 2 field line current, you see the enhanced in the westward convection, and when it is decreasing and this convection kind of disappear, and when it is enhanced again, and this convection repair again. So you can see the region 2 field line current is a very important factor in controlling this westward flow in the subauroral region. So now, because the region 2 links the ionosphere with the inner manosphere, now here I'm showing you the inner manosphere dynamics. The top row is the rain current pressure. The second one is the electric field in the radial direction. And this one is electric potential in the inner manosphere. So you can see after the storm starts, the particles from plasma sheet moves towards the Earth, and they convect. The ions moves westward and electron moves eastward, and the rain current pressure is mostly contributed by the ions. So you can see those the partial rain current develops, and the peak of this partial rain current moves toward the dusk side. That means that the region 2 field line current will also move this direction because it closes this partial rain current with the ionosphere. And in the ionosphere, I just mentioned that we did see the westward rotation of the region 2 field line current. And this is electric field in the radial direction. So previously we see that there's a large poleward electric field in the subauroral region, like here. when it is mapped down to the inner manosphere, you will see a radial outward electric field in this region between 2.5 to L of 4, like in this region. And this largely enhanced electric field is because of the shielding effect of the region 2. So as you can see from these potential contour lines here, so outside L of 4, you see the contour lines is in the day-night direction. Those are the convection, it corresponds to the convection electric field. But when you move closer to the Earth, you see those contour lines trying to scurry westward, and those contour lines move closer to each other, and this corresponds to a large electric field, which is radially outward. And next, I want to show some comparison with some observations. So first one is the comparison with field line currents derived from the AMPERE. So the top two are from the AMPERE field line current. You can see the typical pattern of the region 1 and the region 2. And in the model, we can see also the same pattern, but the region 2 is kind of weaker than the observation. In the storm time, the observation shows very fine structure, but you can see that the both region 1 and region 2, they are enhanced and they expand to a lower latitude. And also, this region 2 field line current is rotate towards westward direction. And in the model, we did see such a rotation. And as I explained earlier, that this is due to the ring current development in the inner manosphere. And next, I want to compare with the MSP ion drift velocity. So each column here shows for one satellite. This is for F17, this is for F18. And there are two consecutive orbits with about 30 minutes apart. So this satellite crossed the polar cap in the northern hemisphere from dusk side towards the downside. So those ovals show this westward flow in the SAPS region in the dusk side. So the model is shown in the dashed line, and the black solid line is the data. So you can see we capture the location and the weight of this SAPS flow. However, we underestimate in the magnitude of this flow. And in addition, those data shows like a two peak profile in the velocity, but in the model we only reproduce one peak. But however, as I mentioned from a previous slide, that we do see the two westward flow channels. But here, for the comparison at a particular time and the location, we do not see such a two peak profile. This means that the SAPS is very dynamic, and our model is able to reproduce this general behavior, but not at this particular time and location. So finally, I want to compare with the Van Allen probe, the electric field measurement. So here I'm showing a movie of the electric field in the radial direction from 9 to 11 UT, a small time period. So this electric field in the radial direction, you can see this channel is very dynamic. The width changes in time, and also the peak of this channel also shifts in the local time. You may notice there's a black dot moving from day side towards the night side. That's the trajectory of the Van Allen probe B projected to the equator. So here is a comparison of this measurement from the Van Allen probe B, which is in the black line, and the red one is from the model. So you can see our model captures this magnitude of the SAPS electric field, which is around 10, and also the location is kind of okay, and it's around 3 Earth radii. But clearly, you can see that the width of the SAPS channel is different. The model shows about 1 Earth radii wide in this SAPS electric field, but the data shows about a quarter RE. So this can be caused by several reasons. One is that in the model, the inner boundary of this ring current is much closer to the Earth, so that we see those. The region 2 is more closer to the Earth. That's why the electric field is also closer to the Earth. Another reason may be in the model itself, because our model in the equator has a resolution of a quarter RE, and this means that we could not resolve features smaller or equal to like a quarter RE. So in the future, we probably will refine this resolution in space and trying to see whether that could improve the comparisons. So to summarize my talk here, we investigate this temporal and spatial evolution of the SAPS in both the ionosphere and in the inner magnetosphere. And we found that when the shock arrives, the ring current develops, and the region 2 field line current is enhanced. And this electric potential cell in the ionosphere tends to extend to the lower latitude and separate from the main auroral convection cell. And that results two westward flow channels, and one is the SAPS channel. And the inner magnetosphere also experience large radial electric field. So we also compared with the observations. So the ionosphere field line current shows consistent picture with the AMPERE, and also the flow, the SAPS flow is reasonably captured when compared to the DMSP, but we underestimate its magnitude. And finally, the inner magnetosphere SAPS electric field is also reproduced in terms of the magnitude and the location, but we have issue in the width of the channel. Thank you.
Questions, John?
I'm coming, John.
It's a very nice study. On your comparisons with DMSP, where you see the width of the SAPS channel, but you don't see the amplitude and you see structure, what we were showing yesterday is some of the wave-like SAID structure that's within the SAPS channel. And I guess one of the things I pointed out in my talk yesterday is, and what we've said before, is when we see SAID, which are the narrow, very intense features, they're wave-like features that are embedded in the SAPS channel. So looking at the ring current itself, you're going to see the overall SAPS channel. The second thing is that 10 UT spike that you modeled for the March 17th. That's got to be a real tough one to work on. So you did a very good job getting that magnitude.
Thank you. Yeah, that's very narrow. Yeah, spike is.
Does the precipitation model in the model include diffuse electron precipitation?
We only, no, actually no. So we only specify the conductance as a function of the field line current. So if we have the field line current, both region 1 and region 2, we assume that there is a precipitation at this region, but we do not explicitly specify the precipitation.
Okay, thank you.